So going back to that Trig relationship we talked about, we have the local displacements, and if we have the Trig relationship, that gets them over to the global coordinates. So how do we get from the local to the global? We have to do cosine theta of the local displacement at node I in the x direction minus the local displacement at node I in the y direction, sine theta there, and we get the global displacement in the in the x direction at node I. Now you can see here, hopefully, that we got kind of a system of equations. We can put that into matrix form. All right, so we have our global coordinates for our element, and we have the local coordinates for our element, and we have this new t. All right, this t is going to be called our transformation matrix. All right, so looking at the next page here, again, it's just going to involve this cosine and sines that we have here. So they're the same cosines and sines, and you can track back to the previous slide and see how you have the different local versus global coordinates going on there. But this is the transformation matrix, because what it does is it transforms our local coordinates into our global coordinates. It does it with the displacements as well as with the forces. So the transformation matrix transforms local values into global values. This is going to be very key for what we're doing here, kind of moving between the different coordinate systems. All right, so if we look at our truss element, look at both the forces and displacements. The forces we can get from the change in displacement multiplied times the stiffness of our element. Right? And because we're looking at trusses, there are only two force members along the axis. So we're only interested in the displacements in the x direction, the local x direction. Right? So the forces that we're going to have at node I in the x direction is going to be k times the change in displacement along our member, and as well as the forces at node j in the x direction are going to be the displacements in the along the member only in the x direction. So we're not looking at any forces in the y direction in the local coordinate system. We're local to the member, just this one particular member. All right, so if we put that in matrix form, right, so we'll have, just looking at this, the force, and then we have the stiffness. So here's the stiffness, positive stiffness, and then we have, and then negative is going to be, as you multiply and distribute this K3, you're going to get a negative value there. And we have the same thing for our force at node J in the x direction, so we get the minus K there and the positive K. Right? So again, these K's going back, we said for a member, and looking at our statics analysis with stress and strain, is it's AE over L for our equivalent stiffness for a member. All right, so notice the matrix equation form. We got these local forces equals the stiffness matrix times our local displacements. We're going to convert these over to global coordinates because we need to, again, this is one element and we need to attach it to all the other elements making up the whole system, the whole truss frame system. All right, so we know that the global force, we can get to the global force and we can get to the global displacement if we multiply the local displacement and the local force by our transformation matrix. All right, so we know that. And so if we take the inverse of our transformation matrix, we multiply both sides by the inverse of the transformation matrix, we end up with this on the left-hand side, and the inverse times the inverse transformation matrix times the transformation matrix gives you the identity matrix. So basically there's just a 1 right here after you do the multiplication, and there's a 1 right here. All right, so that's why you don't see anything on the right-hand side there. All right, so if we substitute into this equation or substitute what we just saw for here, right? So we just saw for these two equations. If we substitute this back into this equation up top here, right? So F becomes the inverse of the transformation matrix times the global force equals, substituting in for the local U, we got the inverse of the transformation matrix times our global displacements. Right? Now we multiply both sides by the transformation matrix. So multiply these two together, that's going to give us the identity matrix, and they're going to go away. And again, we're multiplying by the leftmost side to make sure we're consistent on our matrix math. So then we get the transformation there, and so we end up with how we can get the global coordinate form based from our element stiffness matrix. All right? So you'll see what it is on the next slide. But again, we've seen all this stuff before, so what's different? Let's watch what happens here. By the way, so here's the inverse transformation matrix, just so you know. In this case, it's just the transform of the transformation matrix. So a lot of transformation, transforms, a lot of similar terms here, but just make sure you understand which is which. All right, so just noting here what the inverse transformation matrix is. All right, so we're going to substitute the transformation matrix, the local stiffness matrix, the inverse of the transformation matrix, all into our equation we just came up with, and it simplifies to this. All right, so we got all our global forces over here. Again, this is just I and J, so this is just for one member. All right, and then over here we have our global displacements at the nodes on either side of our member. And now what we have here in the middle is our global stiffness matrix for one element. Right? It's not the global stiffness matrix for the whole system, it's just for one element. Right? So it relates the applied forces and the stiffnesses and the displacements for one element, all in the global coordinate system. All right? The k we had before was a lowercase k up here, because this k was not in the global stiffness matrix form, it was in the local stiffness form. So the global stiffness form, we're changing our k to a capital K. And I'm going to have a separate presentation that goes through all these of what's local, what's global, and what is local versus global coordinate system, and what is local versus global form. See, and note with, I'll try to do that my best in the presentation here, but I also have a separate presentation just on that